So I think this is where we were at the end of last lesson. We were talking about the forces on a conductor moving in a magnetic field. So this, of course, is topic 11, electromagnetic induction. So these are the symbols for magnetic field. It's moving a conductor in a region of magnetic field. So we looked last lesson at the force on a positive charge. As the positive charge is moving across, it experiences a force, and Crystal told us earlier that that force is given by QVB. QVB, but it doesn't matter what order you have them in. So the positive charge will experience a force in the upward direction. Current, field, force. Hang on. Current, field, and force. Alright? Similarly, we consider a negative charge. So as we move this across, there are billions of positive charges and there are billions of negative charges. What's happening to a negative charge in there? So a negative charge, as it moves across, the current is in the opposite direction. Current is defined as the direction that the positive charge is moving. Negative charge moving like that, current like that. Field is still in the page, force is down. So the negative charges will be pushed downwards. Either way, and of course it's the positive charges aren't moving. So for those people who have already been through this once, so by all means listen again, but if you copy this down or do something else, that's fine too. Negative charge is moving down, positive charge is moving up. Positive charges are moving, but as the negatives leave here, it leaves the top with a balance of positive charge anyway. So the positive charges are not moving, but it doesn't matter. We're still getting positives up the top, negatives down the bottom. But not all of them. You're not going to have all the positives go up there and all the negatives go down there. That would be a huge separation of charge, and the forces involved in that would be huge. All right. As the conductor is moving with speed v, charges will separate until an equilibrium is reached. So as I was talking to the others before, this positive charge, it wants to move up. But, because there's a magnetic force pushing it up. But there's all these positive charges already up there, and as this positive charge wants to move up, they say, no, move down. And pushing away, repelling. Or the negative charge saying, come down here, attract, come towards this. So you've got a balance of those two forces. The magnetic force trying to push that positive charge up, and the electric force trying to push the force the positive charge down. And of course, the opposite is true for negative charges, which are the ones that are moving. So the two forces must be balanced. Dave?
Which one is stronger?
Which one is stronger? We reach the point where they're equal. All right? And if the magnetic force was still greater, then more charges would move. If the magnetic force was weaker, and the electric force was stronger, then the charges would come back down and we'd have less voltage there. So we reach an equilibrium of those two forces. The magnetic force, FM, the magnetic force, is given by QVB, which Crystal's told us several times. The electric force is maybe a little bit harder to visualise or to understand. It's caused because there's that separation of charge. If we've got a neutral rod, then a positive charge or a negative charge can move along through that, and there's no electrostatic or electric force on it. But if we've already got some positive charges up here and some negative charges there, then there is that repulsion force or the attraction force that's acting on that positive charge. The electric force is caused by the separation of charges already. Does that make sense? Yes, so there's already that separation of charges. The top is positively charged, so repels another positive charge wanting to move up there. Because of the separation of charge, there's a voltage or potential difference or induced EMF, V or E for the induced EMF, between the top and the bottom. So we've got a voltage or potential difference between the top and the bottom. Okay? We've got length L, so it's just like parallel plates. The electric field between parallel plates is V over D. The electric field in this conductor is V over L. So the electric field is V over L. we know that the force acting on a charged particle in an electric field is given by F equals QE, and so F equals Q times V on L. Alright? Those two forces are equal. The electrostatic force QV on L is balanced by the magnetic force QVB. QV on L equals QVB, Q's cancel out, V on L equals VV, so V equals VVL. The voltage that's induced, the EMF that's induced is equal to VVL or VLV, you often see that written. Does that make sense? Okay, let's continue on. Oh, maybe you didn't get that last bit over there. Swinging back to the front of the first board in mode. Can you see that final section there now on?
Yes.
Now, I'm swinging back to the first one shortly. Right. Okay, so note that the EMF will only be induced if there's relative movement. Alright, so here I'm moving a conductor into the field, just as we did before. I could have moved a magnet near a metal rod, and that would have induced an EMF as well. Alright? But it also, so there's conductor moving field, magnet moving near conductor. That's a little bit trickier, and we'll get to that. But it'll only be induced if the movement is perpendicular to the field. So here I'm moving and cutting across the field lines. The direction of motion is like that, the direction of the field is like that, so they are perpendicular to each other. I'm sorry. There we go, just blocked David. So we're only going to get an EMF if there's some motion perpendicular to it. In this case here, we're moving in this direction and the field is in this direction. And you may recall from when that was covered earlier in the course that a particle will only experience a magnetic force. So F equals QVB, Crystal told us lots of times. But of course there's a bit more to the formula to that crystal, isn't there? What else is in the formula? F equals QVB sine theta. Thank you, Phi, and thank you, the latency crystal. So it does depend on the angle as well. And if we're going parallel, whether it's just a charged particle moving, so we've looked at electrons or protons moving parallel to magnetic fields or perpendicular to magnetic fields, and they'll only experience a force if there's at least some component of them travelling perpendicular to the field. Okay? So if the field is in this direction and the particle comes along like that, it doesn't experience a force. Or like that, it doesn't experience a force. If the particle is moving like that, it experiences a magnetic force. If that's the field and that's the current, then the current field force will be up. Alright? And if it was at an angle like this, then part of it is perpendicular and part of it is parallel. And so what we get is, just like with projectile motion, the bit that's parallel would experience no force, so that would keep on going, and the other bit would get circled, so it would end up with like a spring or a spiral or a helix, a helical path. I haven't seen any questions on that for a long time, but so let me just go through that again. Sorry, camera, and I left you here looking at that. So, if we've got motion, so if there's the magnetic field, the red, and that's the arrow. If the particle is moving like this or like this, no deflection, no magnetic force. If the particle is moving like that, and again let's assume that that's the direction of current, so a positive charge moving that way, that's the field, so current, field, force would be up. It would experience a force up. As it moves up and gets to this position here, now we've got current, field, force. The force is always perpendicular, so it would actually go in a circular path because the force is always perpendicular to the motion. If we combine both of those together so that it was coming in at an angle like that, first of all, if it came in at an angle like that, it's still perpendicular to the field, so it would still go around, other way around like that. Alright? But if it came in at an angle like this, part of it is parallel to the field, it's going to experience no force. Part of it is perpendicular to the field, and it will experience a force. And so that bit keeps on going, the other bit doesn't circle, so we've really got, like that, a spring or spiral or helical shape. Okay? Again, that's, I haven't seen a question like that for a long, long time. Okay? Alright, so we're going to get relative movement. Okay, so
Thì đỡ được. Cái 500 đô này là của cái Medibank rồi năm ngoái gửi tàu mà nó gửi đâu. Cái gần 500 đô ta nhận được là của Medibank.
okay, have you heard the term magnetic flux before? You've heard of magnetic flux? Good. Okay, so magnetic flux, we talk about electric flux as well, but flux is a measure of the, the concentration of field lines going through a particular area.
You'll be famous. Không nhìn thấy tao. Không chết này.
Okay, so magnetic flux, it's not a new section, well, it's new to you, but it's not, you know, we haven't left behind this first part. This will feed back into the first part now. So magnetic field is measured in Tesla, you're comfortable with that, hopefully. Magnetic flux is a measure of how much magnetic field passes through a given area. So I've got these field lines passing through a rectangular loop of area A, square metres. Magnetic flux is that symbol, phi b. You've come across phi before in maths. You know, we often talk about theta and then phi. That's small phi and that's capital phi. Alright? So phi b, because of that subscript, just like before we had you know, the Fm and Fe, the magnetic force and the electric force. This is phi b for magnetic flux. You're not going to have any questions on electric flux, but magnetic flux, so don't worry about it. Phi b is just equal to B times A. Alright? However, this is only true if, Rosie, what? I've said that the magnetic flux is equal to B times A. This is only true if. Right. Yeah, that's good.
So this one is how many
So, as Rosie told us, that's only true if the field and the area are perpendicular. So here they are perpendicular. So phi is equal to B times A. Here, somewhere in between, it's not perpendicular. And here, the flux is 0. effectively we're measuring what's going through it. So as I rotate that coil like that, the field is coming down, we're getting maximum. By the time we get to here, we're getting not as much going through it. I mean, it's really like the shadow that's cast. Imagine the sun coming from above and the shadow down here. Shadow is smaller, shadow is 0, if it's infinite. Okay? So, now in fact, the book will tell you that, phi b is equal to BA cos theta. But, it depends how we define the angle, and they'll always try and trick you. So, theta in that case, what they're saying is if it's cos theta, what's the angle of the area? In fact, the angle of the area is often defined as being perpendicular to the area. So here, there's the angle of the area, so they're parallel. And that was why I hesitated on your answer, Rosie, but I mean, effectively it's correct. So, in this case the angle would be 0, cos 0 is 1, so we get maximum. In this case, the angle is 90, cos 90 is 0, so we get 0. So, but they will often give you the angle not from the normal, but from the surface. And so, rather than remembering, so I'm going to say phi b equals BA cos theta or BA sin theta, depending on the angle, and just look at the angle and, is it appropriate to use sine or cos in this case?
What angle is it? Is the angle right?
So if we use theta equals BA cos theta, which I think is what your data book tells you, then the angle is measured between the normal to the area, normal to the plane, and the magnetic field. So I guess in this case, well, whether the angle is 0 or 180, it doesn't make any difference because, well, cos of that is 1 or negative 1, isn't it? And it's still not going to affect the magnitude of the EMF. Okay, fair question. Okay. And so I think I just leave it at that, that you just need to be careful how that angle is defined. All right? Is it defined from the normal, or is it defined from the plane of the plane? And just sort of think, right? If theta got to 90 degrees, what does that mean? Does that mean that it's 0, or does it mean it's a maximum? So by saying f equals that BA cos theta, then you've got a 50-50 chance of just relying on that and getting it wrong. So better to look at the situation.
So if they're perpendicular to your components.
If what? So, like in the first case, if the field is going all the way through, as you go, if the shadow that's cast is the maximum, then the flux is the maximum. So, I've got the light shining from above, the sunlight shining from above, and the shadow on the ground is large. As I rotate that, the shadow on the ground is smaller. As I rotate it more, the shadow on the ground now is 0. So flux is maximum, flux is in between 0 and maximum, flux is 0. Does that make sense? Yeah, so it just, 50% of the time they'll define the angles, they'll show the angles in different ways to try and trick you, because some people will just say, oh, BA cos theta, and there's your first option. But sometimes it's cos, sometimes it's sine, depending on which angle is shown.
So
when we use cos theta?
Okay, so clearly in that situation, the flux is a maximum, all right? If it were at some angle, all right, what angle is that at? Am I measuring this angle here, or am I measuring this angle here? And so in one of those it will be cos and one will be sine. Let's assume this angle here, so it's at a small angle, so we're measuring this angle here, it looks like about 20 degrees. We're close to maximum, aren't we? If it was round like this, So if this angle was 70 degrees, then it would be close to minimum, close to 0. So if we've gone up just a little bit, and that angle is 20 degrees, all right, we're going to use cos or sine. If the angle was 0, then I'd be maximum. Cos of 0 as well, so cos is what I want. It's that angle there that's shown. But if it's this angle here that's shown, if that, you know, again, if the angle is 90 here, then that's maximum, so I'm going to use sine for that one. Does that help? Yeah, you'll have a go at a few of those different questions about how much or whether there's anything there or not. So, don't sweat too much, but just look carefully at the ones and the questions that they throw at you. All right. What's the units? Oh, yes.
I cannot see you.
Oh, no, I can't see you either. Oh, but I'll let you see everyone else. Yeah. Hello, Diana. Hello, Rosie. Hello, Crystal. Hello, Vincent at the back and Fee. Hello to Brian. Hey, we've got a couple of intruders up the back. So hello to you then. And hello to Lily.
Hello.
And there. And this is on. Okay. So, well, I was just trying to explain again about this angle here, why sometimes it's cos and sometimes it's sine. In your data booklet, it will tell you cos theta. But that's because, technically, the angle is defined as that. The angle of that plane is there, because that's the normal to the plane. So cos theta, if the angle is shown between the normal to the plane and the direction of the field. But often they'll show up not between the normal to the plane of the field, but between the plane and the field. And then that will be the opposite angle, and instead of cos, you would use sine. So that's why we made a bit of a song and dance of it, but that's what's shown in your data booklet, but sometimes it's that, or sometimes you've got to change the angle around. So we'll come across that. You'll see some different questions, and some of you will get fooled, and some of you won't, and by the end of the year, none of you will. Maybe. Okay, what's the units, Diana, of flux? Units of magnetic flux? Not R, no. Or not either. Okay, so, not surprisingly you don't know the units, but, you can still work out the units from any equation that involves it. Alright? And we've got an equation here. So this one here. So therefore, the units of magnetic flux are... Sorry, I can't hear you. Yes. Not Tesla per meter squared, but exactly as you said, Tesla times area, Tesla meter squared. But that has its own unit as well. Just like we could say the unit of force is the kilogram metre per second squared, F equals MA, but that's a Newton. There's a unit of magnetic flux named after a famous scientist. In fact, named after a famous maths and physics teacher at this school. Who? A Stewart. Right. It's the right. What else could it be?
It's a colour.
A colour? No, it's not that. Who else? This is a bit of an obscure one, but maybe you're not aware of this.
Dr. Taylor.
Dr. Taylor, good guess, but not right.
What's the language?
No, good guesses.
What's the rapper?
Who?
Weber?
Yes. It's not named after Mr. Weber, but it's the same name. And I think Mr. Weber might have a double D. But Mr. Weber has taught physics before, and certainly maths before. I'm not sure what he's teaching now. I think his name has a double B, this one has only one, and it comes from the German or Austrian, and so it becomes a Weber. But you can just call it a Weber, no worries. And the symbol is a WB. You can't have a W because that's already taken up by watts, isn't it? So a WB.
Hey, can I take a picture?
You certainly can. So rearranging that, what's another unit for magnetic field intensity, Dave?
Magnetic field intensity. Just it's Weber wait, what? Magnetic field strength B.
Yes?
Is
You nearly got it. I don't think you got it.
Weber per meter. Per area, per meter.
Thank you. That's good. So, the unit for magnetic flux is the Weber, or Weber, WB. So therefore, an equivalent unit, since phi b equals b times a, b equals phi b over a, and David correctly, after a bit of rushing around, told us that the units for magnetic field were flux over area, so Weber per metre squared. Weber per metre squared. And again, don't worry about Weber. You know, that's a German pronunciation. So Weber or Weber per metre squared. Oh, sorry, what? I keep forgetting. So one day I'm going to leave you here and you'll be stuck here all night. Doesn't make sense. Okay. So magnetic flux intensity. Where am I going? All right. So.
Pretty good.
Exactly 2 games.
Nó theo học sinh của Henry ông đấy mà chưa kẹo rồi. Mình bị đánh rồi.
Vincent, but everyone else I've got. And I'll do my best to get those marked over the weekend. And hopefully back to you on Monday. And then we'll give you a full week then to act on the recommendations that I've made. So I'm going to mark them as if I was marking these ones right now. And I dare say some of you will get 8 or 10 out of 24, and some of you might get 16 or 18 out of 24. So that's okay. And that's of course not your final mark, because then, well, first of all it's me marking them, and someone else might think they're better or worse. But so then I'll make some comments, say, well, I've given you 1 out of 6 for this criterion because you haven't mentioned this, you haven't done this, you haven't done this. Make sure you include that in it. All right, and so we'll talk about that next week when we go through. Okay, I'll give you a moment to catch up with this. What do we got? Oh, that clock's probably slow, isn't it? What are we up to? 2:14. Oh, that's pretty good. And it doesn't work. This is Mr. Kerr's specialty. He loves this. And so I've grabbed it from over there just to charge up my calculator, but it wasn't charging. Stick it in there, nothing was happening. I felt like throwing the whole thing out. Mr. Kerr, what are you doing? But then I finally got away with charge. Anyone else who needs calculators charged? So this is I mean, we're nearly out of time now, but perhaps, oh no, you'll need it next Friday when you're doing that. So next Friday you're doing the test, while the standard levels are doing their exam. Right. So the standard levels have been doing brilliantly on their past papers. But I'm not sure how genuine, so some people have been getting 80s and 90%. Some, I think, was there 100% for one of them? so either those standard level students are brilliant, or they're looking at mark schemes. And so I do believe that a number of them are looking at mark schemes. So they will do an exam next week under exam conditions where they're not looking at mark schemes. And I mean, that'll come to you as well. And so when we finish the course, and I reckon we might even finish a week before the middle of the year, year, and so then I'll give you a couple of papers to do over the mid-year break. Whether we start a week earlier on the option or not, I'm not sure, but yeah, we're going on pretty well. Yeah, better than I expected. Where was I going? Oh yeah, so when you do the practice papers,
Is that changing or charging?
the amount of flux is changing. Yeah, good question. Yeah, my changings always look like charging, don't they? So when you come to doing practice papers, I expect that the first practice paper you get, most of you will get 30%. And that's fair enough. The first time you're trying to cover a 2-year course, you're going to forget lots of stuff. They say, oh, I don't know if we've ever done this, or whatever. But you will get, some of you will get 40 or 50, some of you will get 15 or 20. Okay, but at least that's genuine. And if you, I'm not sure about this one. Further the mark scheme. Well, I don't know. 95%. Great job. You're really doing well. I think you should get it. No, I'm not picking on David. But you should get a 7 at the end of the year, no problems. Then comes to a real test and he gets, a 3 or a 4. Again, nothing about you. So it needs to be genuine. And of course you've got access. I mean, I could cover over the exam so that you didn't know what year it was from, or mix them together from different years. And you guys will still find a way around it anyway. So it's it becomes a bit pointless me marking them if you've just copied the exam, put the answers out of something, and B, it doesn't give you or me an indication. I don't know why I'm having to go at you. You haven't done this at all, and then some of the SAM levels are really doing it legitimately. Okay, so I think we've still got 5 minutes or so left. The amount of flux is changing. What's the flux going to look like? The flux time graph here. Please, who haven't we heard from today? I don't think we've heard from David much today. What's the flux time graph going to look like?
It's going to be like 0.
So it's 0 and a constant 0 to start with.
Straight up.
Straight line up?
No.
Curved line up.
Yeah.
Okay? So if we assume we are moving at constant speed, alright? So as this area comes in, so we've got the loop moving in. No. Right, so we'll do it this way so that it all fits in. So at the moment there's no flux. Now there's a little bit. Now there's a bit more. Now there's a bit more. Now there's a bit more. And as it moves through here, it's going to keep a constant value, and then a bit less, 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 0 and a constant 0. Alright? So it should go up linearly, and then constant. How long is it constant for? Well, not long, it's not shown there, but that time and that time are not necessarily the same, but presumably that time and that time are and then 0 again.
Cái skill set mà cần thiết thì mình thi ACE bằng không.
Cái nào chỉ là 100 thì ngon.
Gì theo nhau mày nói thì ra thêm sẽ được thằng
So I know a number of you got maths now. What are we? It's only 20. We've still got time, haven't we? Are we supposed to finish half past or 25 past? Are we supposed to finish at 25 past? Have you got another maths lesson now?
Yes.
Yeah. And is that half past?
2.
Past 2. I didn't think it was half past 3. I thought. Okay. All right. So let's just draw the next graph then. Yeah, negative. I think that's another step, and we'll explain that next lesson. The negative comes from something called Lenz's law, L-E-N-Z.
Is that right?
Yes.
What does it say? Actually, negative rate of
Change. Actually, the negative rate of change. That's where that negative comes from. And David just asked about that. And so the negative is from something called Lenz's law. And so that's important, very significant, but we'll worry about that next lesson. Alright, so where that negative comes from is very significant. Alright, and then just back to look at the graph of EMF against time. So what will the graph look like, please, Brian? Sorry. You want that curve, don't you, Dave? Brian. So, what's another way of saying delta phi b on delta t? Vincent, I haven't asked you a question, but I'll come back to Brian in a moment. Vincent, what's another way of saying delta phi b on delta t? Rate of change. Okay. What's another way of saying it? Gradient. Good. I could have said d phi b dt, dy dx, or gradient. Thank you, Vincent. 2 good answers. Okay. So now, Brian, using the wisdom that Vincent has imparted to you, what's the graph of the EMF going to look like? A decreasing graph. He doesn't like that. So we've got a couple of sections, haven't we? So we've got the first section, second section looks similar, third one looked a bit longer, and then the fourth section. So, hang on. 1, 2, 3, 4, 5. So I can't even count how many sections there are. So 1, 2, 3, 4, and 5 sections, something like that. Okay? So what's the gradient of the first one, Brian? 0. What's the gradient of the second one? Positive. Positive and?
Decreasing.
Is it?
No.
No.
Positive and constant. The gradient is not changing, therefore the EMF is not changing, it's a constant. I could put it as a positive. That negative sign sort of indicates it may be, oops, I should put it like that. What's the gradient of the third section, Brian? What's the gradient of the third section? First section, third section. 0. And I already put the graph back up here anyway. Okay, what about the fourth section, Brian? Keep going. If gradient is negative, so the negative sign means the EMF becomes positive. And it should be equal and opposite to that. And then the fifth section, Brian. There we go. Alright. So we've got an EMF produced here, and an EMF produced here, and 0 for the other ones. We only get an induced EMF or an induced voltage when the flux is changing. When the flux is changing. And so, as that's coming towards the field, nothing's changing. As it's entering the field, it's going from nothing to a bit more, to a bit more, to a lot. It's changing. As it's all in the field, Nothing's changing, no EMF. As it leaves, the EMF, the flux is getting less and less and less. It's changing, so there's an induced EMF. Okay. Yes?
Explain like how you draw the line.
Okay. So Vincent told us that since the EMF is negative delta phi b on delta t, it means it's the negative gradient. Delta phi b on delta t, Om's over here again. Delta phi b on delta t is the same as d phi b on dt, dy, dx, the gradient, the negative gradient. Gradient is 0, gradient is 0, gradient is 0. Gradient is not 0, but it's constant. The gradient is constant and positive. The negative sign therefore means we get a constant negative EMF. Gradient is constant and negative. The negative sign tells us that we get a constant positive EMF. That's what we've got over here. Gradient is 0. Gradient is constant and negative. Gradient is 0. Gradient is constant and positive. Gradient is 0. Okay, people happy with that?
Yeah.
All right. So why there's that negative and other links between a moving conductor, magnetic flux. So we've sort of said that there are two ways of getting magnetic flux, aren't there? By a conductor moving in a magnetic field or by changing the magnetic flux. Essentially they're both the same. They don't look like they're the same to start with, but we'll discover that over the next few lessons. Okay? I said I'd give you some questions, but I think we've got more than enough to keep you busy at the moment, so I haven't. Om's got those questions for topic 11. I haven't done off the rest of those yet. I just sent that to her electronically. But you've got enough to keep yourself busy. So middle of next week I'll give you the questions for topic 11. What are we? Week 4 just finished. Yeah, given that there's no exams, I mean we've got right through. I don't know if they're 9 or 10. Phil, no? How many weeks this term? 9. Okay. Is that using the German? 9. No, so 9 weeks. Okay. So we're not even halfway, and I guess we started on topic 9 a bit earlier than the start of the term. We were doing that partway through the holidays, weren't we? So I reckon we'll go close to finishing. Okay. How about turn the camera on? So